Hello everyone, today I would like to teach on the second order circuit. We are now on part 3. Okay, in the part 3 we will look into the step response for series and parallel RLC circuit. Okay, this is as a revision. As we note in the Salisbury RLC circuit, we already learned about the 3 types of natural response. So there are overdamped response, we have underdamped response, and we have critically damped response. Each of the responses are different in terms of the alpha and omega naught. So the overdamped case is happen when your alpha is greater than omega naught, where you have real and distinct roots. So we have S1 and S2, both are real and distinct. For the underdamped case, it happens when you have your alpha less than omega naught. This is considered as a complex roots where you have real and imaginary number for your S1 and S2. And the third one is the critically damped response where you have your alpha equals to omega naught. This is where your S1 equals to the S2. Okay, this is also a revision for overdamped case. In order for you to have the overdamped response, so the complete solution and its derivative are in the form of Vt equals to A1 exponent S1t plus A2 exponent S2t. And also from this Vt equation, you find the derivative. Okay, in order to solve for A1 and A2, you will need the initial condition V naught and also the dV naught dt. Okay, so we need to substitute the two ICs over is the initial conditions where you have your V naught, and then you replace all your T in the Vt equation equals to 0. So you will have this equation V naught plus, and the V prime 0 positive is actually the derivative for your equation of Vt. So from here you will get your equation of V naught plus and V prime 0 plus. Both are using the initial conditions. So when you have two equations, then you can solve the A1 and A2. Now let's look at the general solution for underdamped response where you have your alpha less than omega naught. Remember that your roots now is a complex conjugate pair. So you have minus alpha plus minus j omega d. Okay, so your omega d is actually the damped frequency. The general solution is formulated as Vt equals to A1 exponent minus alpha plus j omega dt plus A2 exponent minus alpha minus j omega dt. However, this is already formulated into the sine and cosine equation. So we have in the pink highlight there, we have Vt equals to exponent minus alpha t times B1 cos omega dt plus B2 sine omega dt. So how are you going to solve for this B1 and B2? Again we will look into the derivative and also the initial condition. So again, you need the two initial conditions, one at V0 positive, so you substitute all the T in the Vt equation equals to 0, and by that one you get the equation number 1, which gives you B1 equals to V0. And for the derivative of Vt, you will have minus I naught over C minus V naught over RC. Then you solve this two equation to solve for the constant B1 and B2. Now let's look at the critically damped response where your alpha equals to omega naught. So the two identical real roots of S will make your A1 exponent S1 plus A2 exponent S2, but this one is quite not possible. So the general solution is reformulated as Vt equals to exponent minus alpha t times your d1t plus d2. So you can solve again this equation using your initial condition at V0 plus equals to D2 minus V0, and the other one is from the derivatives at the initial condition, and it gives you the second equation. So by solving these two equations, you get your D1 and D2. Now let's look into the 3.4, where you will learn into detail the step response for series RLC circuit. Okay, we named it. You can see that there is R, L, and C connected in series. So this is definitely a series RLC circuit. But you will see that here you have an additional of Vs. So by looking at the switch over there, as t equals to 0, your switch now being closed. Meaning that before that, your switch is open. As your t equals to 0, the switch closed. Now your Vs is connected to the RLC circuit. Alright, so the step response is obtained by the sudden application of the DC source Vs. The second order of expression now becomes your d2v dt2 plus r over l dv dt plus your v over lc, which gives you Vs divided by lc. Right? The above equation has the same form as the equation for your source-free series RLC circuit. In the terms of it has the same coefficients, and however it have different circuit variable in the equation. So the one that different in this one as compared to your source-free is you have Vs divided by LC. Okay, if you look into the details or how you analyze the circuit, we analyze the circuit by using KVL, similar to what you have done with the series RLC circuit, because now you share the same current. So we have the voltage drop at the resistor Ri plus your voltage drop at the inductor, which gives you L di dt, plus your V0 plus 1 over C integration of it dt, which equals to your total voltage supply. Okay, remember that in one closed loop, your voltage drop across each of the components should be equals to your Vs. Now you solve for the homogeneous and inhomogeneous ordinary differential equation it and VCT, and this gives you the d2i dt2 plus r over l di dt plus I over lc equals to 0. And in terms of the voltage, this can be written as d2vc over dt2 plus r over l dvc dt plus vc over lc equals to vs over lc. So you can see over there that your vs is actually the voltage source. Now the solution to this equation, it should have two components. One is regarding the transient response, your Vt, and the other one should be steady state response, PSS. Okay, so if you combine in terms of the equation, it should give you Vt equals to Vt plus VSST. Right? So the transient response is what you have learned in the three cases: the overdamped case, the critically damped case, and also the underdamped case, where the steady state response is actually the final value of Vt. Remember that the final value, if you have any switch, so you should look at the circuit as t greater than 0. Look at the switch and look at the voltage connected to the RLC component. Right? And the values of A1 and A2 are obtained from the initial condition using your initial condition of V0 and dV0 dt. Okay, these are the two initial conditions that should be applied in order for you to solve for A1 and A2. The same concept is applied, even though this is a step response, but you can use the concept of the source-free series RLC circuit. Okay, this is the general solution. Now we substitute your IT equals to A exponent ST into the ODE. we got a different characteristic equation of S, and this one should give you S squared plus R over LS plus 1 over LC equals to 0. And the form of S1, S2 determines the form of general solution. So remember that these are the three general solution of overdamped, critically damped, and underdamped case. And since this is a series RLC circuit, your alpha is also using R over 2L, while your omega naught is equals to 1 over sed LC. If you have your parallel RLC, then only your alpha becomes 1 over 2 RC. The solution is the sum of final voltage and the natural response. So it should give you your VF is the final value and VC nature is the natural response. Now you just combine both. So look at the VF. If you have any voltage source in the circuit, so you just plug in the value into this general solution for the step response of your circuit. So the key points are